Ladies and gentlemen, but it's really just ladies. It's my pleasure to introduce David van Rooij. It's hard to pronounce. David is docked in the Belgica ship. It's just come in, so that's his reason for parachuting into us. So he's just arrived in Galway. Bit of background on David. Apologies for reading this out, but is MSc, Ghent University, dissertation titled Sequence Stratigraphy with High Resolution Seismics along the margins of the Celtic Sea and Porcupine Basin, southwest Ireland. So that's very close to home for us. Then is Advanced MSc, Université de Bretagne Occidentale in France. And then his PhD in Ghent, dissertation titled Integrated Study of Quaternary Sedimentary Processes on the Eastern Slope of the Porcupine Seabed, southwest of Ireland. So he's very much a person interested in sediments and marine sediments just offshore of Western Ireland. He's currently tenure-track lecturer in marine geology and geophysics at the Department of Geology and Soil Science at Ghent University. And he's going to talk to us today about the impact of the Mediterranean outflow water on the Atlantic sedimentary processes and ecosystems. So I'll hand over to David. Thank you very much.
Thank you. And in fact, I'm going to start with something where for me all started with is this wonderful seismic profile. And that is taken in the Porcupine Seabed. This is one of the typical Belgica mounds, cold water coral mounds, on which I did first of all my MSc thesis. These lines were acquired in 1997 with a very small network, and at that time we thought they were barrier reefs. Because what you see in this map, we've got jet probe bathymetry, our own seismics, and that was all the data that we had at that time. Thanks also with Anthony Graham. Over the years, since 1997, there were a lot of European projects towards the Porcupine Seabed, cold water coral mounds, not only in the Porcupine Basin, but also in the Rockall Trough, and further over the European margin. And specifically, these ROV images were taken from the Porcupine Seabed, illustrating very rich fauna of the cold water corals, but something which was more interesting for me are the seabed features, hinting that there are very strong bottom currents. And in fact, the state of the art right now is that we have, and for the moment this is not with the INSS multi-beam bathymetry, but bathymetry that was obtained through the Germans, in Bremerhaven, Toby sidescan sonar, which was partly Annie Wheeler from Cork who was responsible for that. You could see that the Belgica mounds aren't any barrier reefs, but they're now very well known as very large protruding seabed mounds on the eastern part of the Porcupine Seabed. And what at that time was very peculiar, that if you were going to look at the drivers, why are these mounds there? There were two big theories. One theory was proposed by Martin Hofland, connected to the petroleum provinces in the north of the Porcupine Basin, saying that they're being fed by petroleum and gas. And there was another school that said, no, it's more something hydrodynamic, it has more something to do with oceanography. And when we were going to look at the culprit oceanographic process and the water mass, it seemed to be that we have Mediterranean outflow water in the Porcupine Seabed, a very long distance from its proximal area, but still prominent enough to create something on the seabed, to create high bottom currents. And this is a map that I compiled for my PhD with other data, and I think some of Martin White's data is also somewhere in it, where you can see a small zone with enhanced bottom currents on the eastern slope of the Porcupine Seabed, and this falls together with where we have the Mediterranean outflow water, creating internal waves and thus giving large bottom currents there. A compilation work of Christian Dullo in 2009, in fact, plotted all the appearances of live cold water coral mounds on one specific part in potential density envelope, saying that really the occurrence of live cold water cores was immediately linked to a potential density, but it's not all, evidently. So one of my interests from my MSc towards my PhD was, well, we have this Mediterranean outflow water there, but what is the variability of this Mediterranean outflow water, and how does it affect other ecosystems, and are there any ecosystems? Because at that time we knew that there were cold water corals in Porcupine Sea by Rockall, Bay of Biscay, we were not sure, Portuguese margin, Morocco margin, we didn't know. Luckily we had, or I had, a good promoter, Jean-Pierre Henriet, who was very fond in looking at very old publications, and then he found the publication of Le Danois, 1948, which already pinpointed the presence of some cold water coral provinces in the Bay of Biscay. And among others, Anthony Grain went to investigate these things. So for me, it was important to have a look where is the Mediterranean outflow water and what its relation with sediment dynamics and also with ecosystems. So as a small recap on the Mediterranean outflow water, it's a very prominent water mass in the northeast Atlantic Ocean. It has a very large source area in the Mediterranean and a very small origin point at Gibraltar Sea, at the Gibraltar Strait, and there it flows out with an enormous velocity, and it will create a counterite depositional system. We will come back later on that. So, in fact, what happens after Cadiz, or between Cadiz and Porcupine, along this margin, in 1997 we didn't know what it was or what happened. So specifically we were going to look at the margin sedimentary processes and also at the ecosystems. So what am I going to present today? We're going to follow the northern pathway of the Mediterranean outflow water. This little branch here, we're not going to discuss this, but we presume that we have, or we know that we have cold water coral provinces out here as well. Nowadays out of the reach of the Mediterranean, but maybe in glacials it might have been. So we start at the Cadiz reference sites, and then gradually we will move up north towards the Galician margin, the Cantabria margin, the Armorican and the Celtic margin, and then back to the Irish margin to see really the state of the art right now. And we'll also discuss, or I will also quickly point out what the future prospects are regarding the studies of the Mediterranean outflow water over the entire part of the margin. So we'll not discuss any hydrographic processes in detail, but only look at the local effects, how it affects bottom current deposits, and also how it drives ecosystems, and also which type of ecosystems. Mediterranean outflow, this is the classic connection between Mediterranean and the Atlantic. It's not the first time. You also had a paleo connection with the ancient Mediterranean and the ancient Atlantic, but then through the Betic Strait and the Riffian corridor. That ended up through the uplift of the Gibraltar Arc. At the end of the Messinian, the connection was re-established through the Gibraltar Strait. You have an outflow of Mediterranean water between 40 to 200 meters. And the outflow volume evidently strongly controlled by tectonics and also by glacial-static processes. And because of that, this is a 3D block of the Gulf of Cadiz, via Gibraltar Strait, Mediterranean flowing out, and that through the Coriolis force is plastered against the northern slope of the Gulf of Cadiz and creating these very peculiar deposits, which are called in total the counterite depositional system. Counterites are bottom current driven deposits by bottom currents who follow the contour lines, hence these deposits we call them counterites. And counterites are very important markers of oceanographic change. You can use them to infer the flow path of ancient bottom currents and also to see changes in intensity. So they are very powerful recorders of oceanography and also paleoclimate, because in certain positions you have a very high accumulation rate and hopefully not with a lot of erosion surfaces in between. So the outflow velocity at this point is 250 centimeters a second. Pure kinetic energy, pure the water mass flowing down. By the time it's here, the velocity has reduced very significantly, and it will further mix and dilute within the northern Atlantic Ocean. This is a seismic profile that's been taken in one of the sediment drifts or contrite drifts in the Cadiz area, and this is a typical contrite deposit where you can see in fact the several stages of change in evolution of the outflow of the Mediterranean outflow water. This boundary here is the Messinian, so after this boundary you have the onset of the Mediterranean outflow water flow, but then a very sluggish one. And gradually towards the lower Pliocene, you can see an onset, and you can see that the sediment package is forming a wedge. It's pinching out in this location, so we have here the creation of a core of the Mediterranean outflow. And then gradually over the quaternary boundary, this I have to add is an old interpretation where they still have quaternary boundary 1.8 million years, and then upper Pliocene evolution 2.4. It was before the official change from the position of the quaternary. But most importantly, from the middle Pleistocene, there is an enormous intensification of the Mediterranean outflow water, and thus also in the style of this contrite drift. The important thing about that is that we can see a very marked influence of paleoclimatological and orbital parameters within the sediment drift. And if we look at the seismic units from the major sequences towards the minor units, you can all relate them to global cycles in pelotonography. Even in a smaller scale, you can find the Heinrich events back in them influencing depositional styles. So that is the entire picture of the depositional cycles in the Cadiz contrite depositional system. And I will later come back on these, because this is a site that has been studied by especially Spanish investigators. The French have been working there, also the US Navy, and this is very well known. And even very recently, in February or January, February, IUDP has drilled here several holes in order to better have a chronostratigraphic constraint on this entire evolution. But from this point onwards, nothing much was known. So if you look at Cape St. Vincent at this point here, the Mediterranean outflow water is only a velocity of 46 centimeters a second. And when you go even up to Santander, it's reduced to 2 to 3 centimeters a second. And if you take a water sample and you compare it to the Mediterranean, or you compare it to the Mediterranean outflow water in the Gulf of Cadiz, it's severely diluted. And also even within the Bay of Biscay. So in blue is the Armorican deep sea fan, in green is Cape Verde, and in red is Cabo Ortegal. So from the south towards the north, you can see a gradual decrease of, for example, the salinity of the Mediterranean outflow water, so it really gets reduced in strength. Nevertheless, there are sites where we can see that through interaction with obstacles and these internal waves, internal tide system, you can enhance them. And in some of the sites that we discovered in 2004, it's relatively spectacular that you can see this enhancing of the bottom currents, which is, as I said before, a background of 2 to 3 centimeters per second. And one of the areas which is very peculiar is here the Ortegal Cape area, where, so this is a multi-beam bathymetry set that has been acquired with the Belgica, and in fact the Mediterranean outflow water, its upper boundary, is right here, and you can see this very steep point, this very steep escarpment. So for the study of the Mediterranean outflow water, this area was very important. And when we look at the seismic profile, here you can see the start of the Mediterranean outflow water, And when you plot that on the seismics, the interface between Mediterranean and the overlying water mass is really marked with a very strong bottom current, which in fact will expose the entire bedrock, and above you have a gradual sedimentation. And if you look very carefully, you can see here some small bumps, of which we infer that there may be coral patches. So because of the interaction with the topography, we have enhanced currents. And in the entire story of cold water corals, 2 years ago, we stumbled across something new, something interesting, which can also shed a new light on the processes, on the ecosystems. I hope you can see them. You can see some of these small bumps in here. These are small mounds, mini-mounds, 150 to 200 meters wide, 1 to 2 meters high. In the backscatter you can also see them. So this is a little bit blown up, this is up to 2 meters. But with an ROV we dive to them and we can see fossil Lophelia pertusa with a dated age of, let's say, between 9 and 10,000 years. This is something which we discovered in 2010, and before that, every time that we found cold water corals, it was somewhere within the Mediterranean Outflow Water. Now we found them dead in areas really above the Mediterranean Outflow Water, and at ages where you can assume, okay, maybe when it was a glacial period, MIS2, past glacial maximum, they were alive. So the main question is, what happened here? Why did they start out? When did they decay? And for the moment, this is something which I have to leave open and which will be investigated in the future. But what I can say also is these mini-mounds, you can find them right here. And they're surrounded by an entire field of pockmarks. And I'm not going to go into detail, but if you look at or if you compare the size of the pockmarks and the elongation, they totally agree with the size of the mini-mounds and the elongation of the mini-mounds. So there might still be a story with gas, but why do the corals choose that area and not that area? And why we have this remarked relief inversion, nobody knows for the moment. So if we go deeper to where we know that there is the Mediterranean outflow water, the bottom currents are too strong to have anything settled except for this very lone coral, and here with the sponge you can see, or you can estimate a little bit of the strength of the Mediterranean outflow water, at least at that part of the margin. Next step is to the Le Danois, so that's in the middle of the Spanish margin, and if you look at the physiography of the Bay of Biscay, the only thing that you can see is canyons, 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 canyons everywhere. Except for this part. This is a bank that's a little bit detached of the shelf and creates a kind of an intraslope basin. And for over years people have looked over this part. Okay, it's an intraslope basin, nothing new. Until we discovered, or the Spanish discovered with their EcoMar project, they did intensive multi-beam because of a mapping of ecosystems, because this is a well-known fisheries bank, El Cachucho, and they discovered this channel here, and also this channel up here, which has, first of all, different direction than the standard canyons, and also has a smoother surface. So this looked suspicious to us. And if you make a cross-section of the bank in here and in here, you can see that the entire intraslope basin up to a little bit the boundary between the yellow and the brown, you have the Mediterranean outflow water. So in 2004 for the first time, and in 2005 by the Spanish, we did some seismic profiles, so we performed some seismic profiling in this area. And one of the conclusions was that the Mediterranean outflow water bumps on this high, this is the Visco high, and creates 3 branches of Mediterranean outflow. The northern one, which goes north of the bank, and it's very difficult to say that it's really there because we've got all these canyons, very difficult to pinpoint. The central branch coincides with this large channel, and a southern branch also coincides with a channel which runs upslope. But based on multi-beam bathymetry, you can't say a lot on the effect of the Mediterranean on the sedimentary processes. But if you look at air-gun seismic profiles, which have a deep penetration and a medium resolution, we could see the emplacement of two sediment drifts, one here stuck between the Ledama bank and a kind of intra-slope horst, and then a larger drift system which is gradually creeping upslope. And maybe this does not say enough, but if you look at Sparkier seismic profile, which I recorded last year, you can really see in this part, that's this here, a confined drift where you have had bottom currents at either side of this basin, and at a certain moment the bottom current shifted to this part, creating a counter-right drift right here, and another counter-right drift, and I think my pointer has died. Not entirely. Okay, another counter-right drift in that location. And in detail, we could also make subdivisions of 3 units, although we didn't have any chronostratigraphic data. When we only looked at the change of depositional style of the seismic profiles, when we looked at the individual units and the stacking pattern of one unit upon the other, we could draw enormous comparison between the Ledama counter-right depositional system and the Cadiz counter-right depositional system. So, in fact, the south of the Iberian Peninsula and the north, you have 2 sediment deposits which are enormously alike, and especially the Ledama deposit can give a lot of information, if we ever get a drill ship over there, on the timing of what happens in Cadiz and how much does it influence the course of the Mediterranean outflow water and the variability of this water mass and its effect, of course, on ecosystems towards the north. So, in order to understand the Mediterranean outflow water, its evolution, this was a very important step. Then let's go a little bit deeper into ecosystems. In the Bay of Biscay, the only chance to find any ecosystems is to go and have a look in the canyons. You can do as much seismics and multi-beam as you want, but if you don't have any ROV or anything visual, you can't do any good mapping. So in Ghent University we had ROV Genesis. I specifically said had because very recently we turned it over to the VLIS, the Flemish Institute for the Sea, which is good for the European community because now it's more available for other European researchers. And in 2008 and 2006 we investigated 2 canyons, the Gilvinec Canyon and the Le Chapelle margin, and a strange place which we called Ostreasburg. First of all, the Gilvinec Canyon, we had 2 dives, or 2 important dives, here over a flank of a gully and then within a gully, and then this dive over here. This seismic profile already indicated something very strange in this canyon, is that we have a very marked asymmetry in this canyon. It's typically V-shaped, but the northwestern flank has practically no big sedimentary cover. You can see with the diffractions that there are probably a lot of banks, and the southeastern flank is very depositional. And we compare that with sequences which are more located towards the shelf, and these have a Pliocene age. So in fact what we were looking at was, the dive was concentrated on these diffractions to see what kind of lithologies we could find. There's an interpreted track, especially in orange you can see the occurrence of cold water corals. In some places with the crosses, banks or escarpments, banks 20, 30, 50 centimeters thick, escarpments 2 meters, and several places escarpments to 10 meters deep. And then in red, oysters. Something with in 2006 was a surprise to us, but at the same time the German team from André Freiwald also discovered oysters in the Azores Bank. And in fact this was very peculiar to find them at that location. Well, first of all, you have the cold water coral reefs. Some of them, I wouldn't say extinct, but not active anymore. Other of them are active. And you can see that some of the corals are really growing on a dead graveyard of coral. So they form a very open framework, which was in fact interesting for us to see as an analog or a phase in mound building. And that you can consider such a framework of open corals, then a phase where a lot of glacial sediment is put into these corals, and then you can build from one glacial, interglacial phase from a small coral patch to an entire mound. As in the glacier margin, you could also see corals being built up some high relief upon some rocks. And then we saw this flank, which is the same as this one, and we went over the top to have a look. And then you could see these things. So these are the deep water oysters, Neopygmodon sidrovi, which can be 10 to 20 centimeters big. And the Germans dated them at an age they can be 500 to 600 years old. So this is a completely new discovery. And I think we dated, or the depth level, the maximum occurrence of these oysters at the moment is at 800 meters of water depth. This is very peculiar to see, first of all, in the deep sea environment, and it changes a lot also for the knowledge of oysters, because everybody thinks oysters, well, like shallow water stuff, you find one in the geological record, okay, with shallow water. This makes you think twice. Second of all, it's been overlooked for an enormous time. Because when you're doing dredging or you're doing box scoring, most of these oysters, they attached to these vertical cliffs, and then also most of them are seated underneath an overhanging bank. So you can never touch them or you can never observe them unless you have an ROV to document them. The most spectacular find of the oysters was in this location. I think this is effectively the deepest one, where you can see in the seabed fairly high bottom currents, and there you can see them hanging underneath this overhanging bank and some lonely coral which is also there. So in fact, in terms of ecosystem drivers, they very much profit also from the region where you have the cold water corals. And in fact, we discovered them for the first time at that location. It was at that time an unnamed spur. We called them Austria spur, where we had the same setting geologically, and in the dive pattern we also could see, in fact we went to this location to verify the observations of Le Danois. He said that this was plenty of cold water corals. We didn't find any cold water coral except for some fossil debris. But again, that is why, or that is where we found some of these deep water oysters in the first time. If you've been ever to Belgium and you've been on the streets in Ghent or in Brussels, you have these cobblestone pavements. You take this pavement, you put it upright, it's the same as this here. This is a wall of 10 meters high, completely filled with oysters. These of course they're dead, but those, according to my biological colleagues from IFMR, these ones should already or still be alive. If we plot this with the occurrence interval of the cold water corals, this is the occurrence interval of oysters, this is the occurrence of the cold water corals, and that's the occurrence of these mini-mounds. So in the theory of the potential density envelope, we need some fine-tuning. And the fine-tuning can relatively easily be explained if you plot the occurrence again of the Mediterranean outflow water and the overlying water mass on the seismic profiles of, for example, the Gilvinic Canyon. You can see still in two seismic profiles the asymmetry, and you can also see at the boundary of the MOW with the overlying water mass, you can see an intensification of the sediment drift style. And I think it's okay. So you can see here intensification. Moreover, if you look at the flow of the Mediterranean outflow water, it flows from south to north, and we think it flows over the banks, rushes down, loses all its sediment, bounces to this flank, creates erosion, is going over the top again. So in fact, because of the flow of the MOW and the location of the margin, you can create this kind of asymmetry. And in fact, if we performed ROV dives at the other flank, because this was more sedimentary regime where you didn't find any overhanging banks, we couldn't find any of these oysters. So in fact, this study that was published in deep sea research can also contribute in better finding, better locating these ecosystems. Because if you want to study them, you say, okay, they're somewhere in a canyon, but you have only 2 days with an ROV, or better, 10 days with an ROV and 2 good days to do ROV surveying. You need to have the good area to go to. So with seismics, multi-beam, backscatter analysis, and with the correct CTDs, you can find them in the very, or hopefully the good locations. So that was a sketch that I made of the occurrence of the oysters, and then somewhere you can see a lonely cold water coral. What I didn't include in this presentation is the findings that we did in the Withered Canyon a few years ago, of which a colleague of mine in Southampton, Weber Huvenne, published a very nice paper regarding cliffs, but then with cold water corals. So going back to the Belgica province, what does all the knowledge that we had from the Le Danois Contourite depositional system and the rest of the Celtic margin brings us to better understand the evolution of these mounds? And in fact, the first seismic profile, the old one that I showed you, is reprocessed here with a new multi-beam image that we have, and you can see a very nice, little bit blown up 3D block of the Belgica Mound province in the Porcupine Sea bites. So if I would compile the results of all the seismics from 1997 to 2012, and a very important feat was the IODP expedition 307, which drilled through this mound, through this drift deposit, and also through this unit right here. It has given us a lot of information. It has given us information, first of all, on the enormous hiatus or unconformity on which these mounds are rooted. This is an unconformity. This goes from the upper part of the slope, goes down, creates this big channel, and goes up again. And a very nice marker of the impact of this unconformity is you can see this nearly acoustically transparent unit right here, and that's the same right here. So at a certain moment this must have been completely filled. So, and you can also see that here the erosion has evolved a little bit stepwise, like in river terraces. It must have cut in several phases into the margin. During my PhD, I only could have a guess when this was. IDP helped us a little bit refining this. Second of all, after the very large erosional period, we had the installation of, again, sediment drifts in the Porcupine Sea bind, and next to that, or let's say in parallel, we had the introduction of the cold water coral mounds. So, and in fact, what we see is an interplay of phases where we have very high erosion and very high bottom currents, and then it's the question which was first. Did we have the coral mound first, or did we have the drift mound first? And that's something which all the other investigations in the margin helped us. This is again another sketch to better document the impact of the erosion. In yellow is this acoustically transparent layer, and this seismic profile is right here, and you can see that 300 meters, at a certain point 300 meters of sediment have been eroded away, but we didn't know in 2007 the extent of this erosional hiatus. But you could see that in white here it created a big channel, and on the eastern part of the channel, in another shade of yellow, you can see the emplacement of the cold water coral mounds. Thanks to IUDP, we were able to date this hiatus, and dependent on where you are looking, because ideally they should have drilled in this place. But for example, in between the mound base, you have the recent startup of the mound was at 2.4 million years. Is it coincidence that it's 2.4 million years? And the oldest underneath was 16 million years. Now the smallest hiatus that we have is right here, about 7.5 million years. Personal other unpublished data that I have may believe that the duration of the hiatus might be a little bit more shorter, 5 million years, but short. So what did we see in fact across this boundary is first of all a change in bottom water mass regime. Bottom waters, they got severely reduced, the velocity changed from almost nothing to a very high background velocity. If you look at the water mass itself, it became warmer, so that means that from here to here, no Mediterranean outflow, the start of the Mediterranean outflow. And if you look at this thing here, you have to be careful, it's not being dated yet, but these sequences, they look very much like they have a kind of frequency in them. So they might be climatically tuned. So the mound onset was dated at about 2.4, 2.6 million years, beginning of the Quaternary. And on the other hand, the drift onset was coupled at 1.2 million years. So that's about the Middle Pleistocene evolution. So that all falls into the picture that we have of the evolution of the margin. And most of these mounds, they are seated in a very peculiar position on top of the escarpments, exactly the places where you have the highest bottom currents. In red here you can see where the mounds are seated, but they are not the only mounds morphologically. You can also see this blue thing here. This is a drift mound, and it's created in a very peculiar way. It's created by a channel which is artificial. At one side it's created by an escarpment created by the erosional phase of 5 or 7.5 million years. And at the other hand, it's the other flank of the channel is in fact a kind of carbonate mound. And that also enabled us to date the occurrence. Which one was first? Was the mound first or was the drift sedimentation first? And you can see here, so this seismic profile is located in here. You can see very well the artificial channel wall created by all the mounds which are seated next to each other. So if you want to create something like that, first of all the mound must have had a kind of adult stage before you can create something like this, where you have the influence of a current path at the foot of the mound and the foot of the escarpment. So for the porcupine, we also can define a contourite depositional system, as in the Danla, as in the Cadiz margin, but then much more complex, with especially this phase where you have an interaction between contourites, turbidites, and cold water coral growth, and also a very marked connection with paleoclimate. When the erosion started, that's something which we still have a lot of discussion around. Ideally, we would have another IUDP leg in order to confirm that, but anybody would like to have something like this. But we know that the erosion or the bottom current strength severely reduced to allow something to grow at about 2.4 million years. And that at least until 1.2 million years, you only had the growth of cold water coral mounds and nothing else. And then from the Middle Pleistocene evolution, the growth of the cold water coral mounds declined. And from time to time you had a cessation, a stop of growth. You had erosion even on the mound. But you could see a gradual increase of contrite drift deposits, more glacial clay, sandy sediments which are put into the system. and, as in other provinces in the north of the Porcupine seabed, will eventually take over, will bury some of the cold water coral mounds. And in some of the cores that we've acquired over the past 15 years with Marion Dufresne, we can very well see the influence of the change of the Mediterranean outflow during glacial and interglacial times, where during interglacial times we have MOW present now, creating strong bottom currents. This is marine ice flow stage 5 with a very thick sandy contourite. When we go to a glacial period, MOW doesn't flow or is flowing in a reduced way out of the Gibraltar Strait, remains confined in the Gulf of Cadiz, is completely absent, and then we have a muddy contourite in the Porcupine seabed. So in fact, to summarize all this, somewhere in the intra-Pliocene we had very strong currents. From 2.4 million years, currents were more sluggish and allowed the creation of small reefs, growing to small mounds. And then afterwards, at about the mid-Pleistocene evolution, you had more sediments coming into the system. One of the questions you might ask, and I hope, what am I doing now? Why am I in Ireland? On Sunday I'm going to leave to Gobensburg to find yet another clue to better investigate the evolution of these mounds. Because I told you before, there is a very big hiatus, 7 million years. We want to know what happened there, and especially to find out if this acted in several phases. And one of the clues might be located here at the old DSDP site. In fact, it was the first oceanographic leg for DSDP, but if you look at the publications, they didn't do a lot with it. If you go to Bremen, you look at the cores, they're pristine. Nothing happened with them. This is an old seismic profile from the 80s. In 2001, we went back with our own spark, and we could see this is what they had, and this is what we can see. We can see several unconformities. So maybe we can reinvestigate the core, link them to the unconformities, and maybe some of these unconformities can be linked within that period of 7 million years. So we can better estimate the dynamics and better correlate that with the real mound people have obtained of studies within the cold water coral mounds. That's one of the studies that's originated very recently from this DSDP site, where we can see that at 3.3 million years you have an enhancement of the Mediterranean outflow water. And that still is in the region where we have our erosion. And you can see from time to time, you can see these wavy sediments. We also suspect that the MOW on Gobensburg is very dynamic and can create kind of sediment drift deposits. So in fact, to summarize, we can see from Cadiz to the Porcupine very big similarities, which are driven both for sediment as for ecosystems by the Mediterranean outflow water, where we can really very well compare Cadiz with Le Damba. For Porcupine, we've got a problem because we have to look at two records, which are discontinuous, the mound at one side and the drift at the other side. And maybe in between here, I have to, or hopefully, can put within a few years the Gobensburg site. This is something which I leave. Another thing, which if you're more interested in the Mediterranean outflow water, is the very recent leg which has been drilled in the Gulf of Cadiz by Javier Hernandez Molina and Loic Stowe. This is a picture of the joy that's taken immediately after this campaign. So they drilled at several sites in the contourite drift, in the contourite depositional system. So this is now in the process of being studied. The moratorium is still present, but if there are people interested, I think within 1 year it opens, and then maybe some Irish people can join this study. So that's all. If you've got questions, shoot.
Thank you very much, David. That was a very enjoyable, very engaging talk.
You're welcome.
Any questions?
I was just going to say, there's only something I was thinking on the way in the car. We have a paper in press at the moment that we've looked at the carbon chemistry of the water masses in the Rockall Trough, and the Mediterranean water has a high alkalinity signal. So that that could mean that this water mass would have, it could like buffer some of the changes that will occur with ocean acidification. So maybe the corals that are present along the, in the vicinity of this water mass might actually benefit from being in this high alkalinity water because they won't, the pH won't drop as fast as it would in elsewhere. So I don't know whether that would have any kind
It might actively encourage their growth if
Yeah.
the water is more alkaline. That's
Yeah,
something
sure.
that
Because for the moment, what we don't know is, we know how the MOW evolved in the Gulf of Cadiz. There is a study of Schoenfeld in 2002 towards the Portuguese margin, and he says, okay, there it stops. But any more information on what MOW does in the glacials, or how fast is it reintroduced and what its effects are, we don't know. So now I have 2 PhD students. One is looking at CT scans of contrite sequences, and another one is really tracing on several sites with neodymium isotopes to see really when this MOW coming back there, has it ever been there, and what's the effect for bottom currents, and that might very nicely link with what you're doing.
because our stuff is all now, because it's oceanography rather than paleoceanography. But it's interesting to think about.
it could have.
That it actually
Regarding
would enhance
oceanography, something which I would like to give along on anything what is related with bottom currents. Very recently we have an IGCP approved on bottom currents and contorites for the entire geological record, and next to it we have an INQUA project on contorites, but then for the quaternary. This is going to last hopefully for 5 years, and what we really hope is to have a better link to oceanographers and geologists. So we will have conferences, workshops. One workshop on oceanography is now being prepared by Mike Rogerson in Hull, hopefully somewhere in January. So with a very large suite of conferences, also a hope to have a kind of training to research campaigns where students interested in the topic can be exchanged. So I'm happy to give you the information for that, because we hope the network to expand. But in Europe we are very well covered, but the rest of the world it's difficult to find somebody. So,
But for us, because you have here geologists, geophysicists and oceanographers, and we're all interested in this region. Certainly once you get into Porcupine and further north, we are all studying whether it's the corals or the water or the geophysical aspects of it. So this is really interesting stuff for us.
It seems to me that your work is very much pointing towards the currents, stimulating the growth of these mounds. And you mentioned at the start the hydrocarbon seep theory. And I can remember years ago when these things were, a long time ago, when these things were initially described, that this was put forward as an idea. What is the state of understanding of that theory at this point in time?
Well,
is it discredited?
it's been weakened. It's not being discredited. First of all, the thing what we discovered with these mini-mounds and the pockmarks, that's something which still triggers our interest. And the part that I left out on the Moroccan margin is very interesting, because there we have small cold water column mounds which are sitting on an escarpment, which is immediately linked to a hydrocarbon reservoir in the deep. We have also in the other side of the Gibraltar Arc at the Melilla Mount province, you can see a beautiful seismic profile with very high amplitude reflectors, a very nice reservoir, and a fault immediately going to the mountains. What is there? Let's say, what's the influence? We think now that it's more a matter of preparing the subsurface, for example, to create carbonate crusts, which allow corals to settle more easy, and also in a way, especially in the Gulf of Cadiz, it's exactly in this area here. We can see they are very small mounds, but they're very much affected by diagenesis. And that means that the corals there are a little bit dissolved, but in fact you can find other minerals and they solidify the entire coral plate. So they may help in strengthening the mount and allowing to build such a large thing. And we will have a Eurofleets campaign to that area, and a MOW campaign, so the German drilling rig, to drill through these mounts to better understand this process. It's present in the Porcupine seabed, but one of the results of IODP is there is no methane. The methane, or the bacterial counts, remarkably, are higher underneath the mount base, underneath the mount than within the mount.
What about CO2 though? Because from our point of view, if you have pockmarks, if you have CO2 hydrates there, you're going to acidify your water, so your corals aren't going to settle. But if a little bit further up or down the slope you have Mediterranean water, which is nice and alkaline, then this is counteracting the acidic effect, and they're really happy there.
Yeah.
So as well as,
the main problem is with these pockmarks, they've also been studied by Dept, and something similar has been studied by Dept. The main thing is what's the driver of these pockmarks. If we look at our seismic profile, we don't see any evidence of something active. Seepage, gas hydrates or hydrates in that area, I don't know. It's near a canyon, maybe it's something related to that, but these are, I'd say, nowadays cold water coral studies. On the one side, you've got a perfect climate story, the article that's been published by Mediterranean in the Quaternary Science Review, where you have within the cold water coral sequence information locked on the glaciation history of Ireland, that's one thing. And then the entire diagenesis story, which is ultimately complex, that's another thing to investigate.
Those mini-mounds, you said they were the eastern margin?
Yeah.
Because we have very similar features in the eastern Porcupine seabed, the mini-mounds.
Yeah.
They look very similar, and I know from Ifremer that they, Jean-François Fabre really contacted us because they found similar things in the Bay of Biscay.
Yeah.
So do you know if there's been any comparative studies? Or?
We've submitted a project to do that.
Oh, okay.
Yes.
Very good.
I've been in contact with Jamie Davies and all the people from the MESH program who in fact discovered I have something up there on the Bay of Biscay. So for as far as I know, well, you've got the Magnus mounts right here. The ones that I shown are right here. The Gilvinec, we also discovered some in this area, and then Mesh is just here at the Irish part at the Dungard Explorer Canyon. Qua depth, it's the same. Size, it's the same, but the appearance at the seabed is different. Here, you really have very well delineed mounts where you have got sediment and very big chunks of corals. Here, and I'm not sure about the Magnus mounts, they're really much more scattered, and you can see coral broken up in bits and pieces over the entire seafloor. There are two questions. Are they genetically related? And B, what's the influence of the fishery? And we know here that there's a lot of fisheries, here it's less. So that's one of the aims of the project, to see A, what's the driver, and what's the relationship with the pockmarks. And then secondly, if they are genetically related in time and in driving processes, why do we have a difference in very small nice mounts here and this completely crushed? Is this related to fisheries or is this not? If you look at the ROV images that we have, you don't see any clear trawling marks. Or is this such a very dynamic area where these trawling marks are erased? But if it's not trawling, which process could we infer that can break up these corals in such a small state? So there are still a lot of questions to be solved on that. And this is pretty important because we think that in order to build these giant mounts, they only occur from here. Here you've got nothing, you've got reefs, you've got the small mounts in Galicia Bank, nothing here, and here still you've got big mounts. But where are the mounts right here? Why not there? There's still a lot of things to do, so we can continue for another 5 to 10 years.
Oh, I also just